So we are going to continue our lecture with chapter 5, which is this chapter is going to cover on mass Bernoulli and energy equations. And actually these three equations are commonly used in fluid mechanics, where the mass equations is explains about the conservation of mass principle. I think you have learned about the conservation of mass since high school, where mass is very similar to energy. It can neither be created nor destroyed. It can just be changed from one form to another form. So basically it's very similar to energy. Meanwhile, for Bernoulli equations, this equations explains about how the relationship between the total energy is like kinetic, which is the summation of kinetic, potential and flow energies in fluid. Okay, and lastly, the energy equations, very similar to mass equations. We will also talk about the conservation of energy principle, and yeah, similar as mass, which is energy. It can neither be created nor destroyed, and it can only be converted from one form to another. Okay, this figure shows an example of like wind turbine farms, which is constructed all around the world to extract kinetic energy and change it into electrical energy. So basically, in these applications, the mass and energy equations are utilized in designing the wind turbine. And Bernoulli also plays a quite important roles in the design stage, where the blade of wind turbine actually is placed. It has quite similar. It's very resembles the airfoil for wing, where, as you know, that wing actually is very important to understand Bernoulli equations when we design wing. So basically, the blade used for wind turbine, it has a similar concept to wing. Okay, the objective of this chapter is to apply the conservation of mass equations to balance the incoming and outgoing flow rates in a system, and to recognize various forms of mechanical energy and work with energy conversions efficiencies, and to understand the use and limitations of the Bernoulli equations and apply it to solve a variety of fluid flow problems. And finally is to work with the energy equations expressed in terms of heads and use it to determine turbine power output and pumping power requirements. So we are going to cover all these four objectives in this chapter. Okay, so like you are already familiar with these all numerous conservation laws, such as conservation of mass, energy and momentum. You have learned this during your high school and during your foundation studies in CFS, and also during your first year, like momentum, you learn in dynamics. So historically, the conservation laws are first applied to a fixed quantity matter called a closed system, or we can also call it as a system, and then extended to regions in space called control volumes. We already cover about this system and volumes at the end of chapter 4, which is the Reynolds transport theorems. So basically chapter 5 is like where we are going to apply what we learned at the end of chapter 4, the Reynolds transport theorems. Okay, so the conservation relations are also called balance equations, since any conserved quantity must balance during a process. Okay, for conservation of mass. So basically the conservation of mass relation for a closed system undergoes a change, and is expressed as m of the system is always constant. So what does it mean by constant? Is so when you differentiate it with respect to time, basically you get zeros because it is constant. It doesn't change with time. So the differentiation of it with respect to time, or the rate of change of the mass in the system with respect to time, is actually equal to 0 because it doesn't change. So that's where we get these equations, where this m dot, actually the dot here is represent the rate of change in time. So this is not only m. If you have only m without dot, that means that it represents mass. If you have dot here, it represents mass flow rates. Okay, the mass flow rate that goes into the system, if minus with the mass flow rate that goes out from the system, you get the rate of change of the mass in the control volume. Oh, I'm sorry, it's not system, it's control volume. It's like mix up a little bit. So the rate of change of, so basically if it is like the in and out is the same, is similar, so you will get this equals to zeros. So like I think I mentioned previously, like in fluid mechanics, most of the time we are going to only like the applications that we are going to apply throughout this fluid mechanics course mostly is where the mass flow rate in is equals to mass flow rate out, especially in internal flow. And so in fluid mechanics, the conservation of mass relation with written for a differential control volume is usually called as continuity equations. We are going to talk about continuity equations in not really like in the next few chapters, if I'm not mistaken. Okay, these are linear momentum equations. Okay, linear momentum is basically the product of the mass and the velocity of a body. Actually, so it basically the product of the mass and velocity is called as linear momentum. You have learned this in dynamics, if not mistaken, where the product of mass and v basically will give you mv. If you remember it clearly, still remember your dynamics, basically mv is equals to momentum. mv is momentum. And yeah, so basically Newton's second law mentions that the acceleration of a body is proportional to the net force acting on it and is inversely proportional to its mass. So basically Newton's second law is actually the one that we use it most of the time, where F equals ma. Actually the Newton's comes from the Newton's second law, where from here basically you can get that A is equals to F over m. So here is where we get it, basically these principles basically is explaining the principle that the acceleration is proportional to the F or force, meanwhile is inversely proportional to the mass. So the rate of change of the momentum of body is equal to the net force acting on the body. So if we go back to this, if F equals to ma, basically F equals to ma, and a, as we know, that is the rate of change of velocity. And if we rewrite this, what you get is dmv over dt. So it is the rate of change of momentum with respect to time. Okay, so yeah, the conservation of momentum principle, it explains that the momentum of a system remains constant only when the net force acting on it is zeros, and thus the momentum of such a system is conserved. If this basically you already applied it, already learned this in your dynamics course, I believe you should have no problems to really understand this conservation of momentum principles. And linear momentum equations in fluid mechanics, Newton's second law is usually referred to as linear momentum equations. Okay, next we go to the conservation of energy. So the conservation of energy principle is where also known as the energy balance. So it's mentioned that the energy transfer to or from a system during a process must be equal to the change in the energy content of the system. So energy can be transferred to or from a closed system by heat or work. So basically this, if you look this closely, actually is very similar to the conservation of mass. So the concept is the same. The energy that goes into the system minus the energy that goes out to, sorry, the control volumes is equals to the rate of change of energy in control volumes with respect to time. So basically it shows that energy in that control volume cannot just suddenly like created, it's not like suddenly appear. It must be due to the energy. There is a source that's supplying the energy into the control volume, and this the control volume also is like, if you suddenly get like the energy in the control volume suddenly like disappear, it doesn't disappear just like that. So it's disappeared because it's being released from the control volumes. Okay, so this is why we get this E out.